Hello and welcome back to the Networking Fundamentals section of this course. In this video, we'll be discussing IPv6 and how to work with a 128-bit address. Now recall that our IPv4 address space is only a 32-bit address field. Now with IPv6, we've expanded that address field to be 128 bits. The primary reason that this was done is because we're simply running out of IPv4 addresses. In fact, there are no longer any unallocated IPv4 addresses. All IPv4 addresses have been allocated and are either in active use or allocated to some organization. So that's put a big scare on a lot of people that we no longer have any addresses available. Now, things like network address translation have allowed us to really use our IPv4 addresses to the fullest extent. With IPv6, though, we have substantially increased our address field and allowed for many, many more addresses. And we'll talk a bit more about just how many there are in the upcoming slides. So let's take a look at an IPv6 address and how we can make this 128-bit field a little more manageable. So the IPv6 address is split up into 8 hextets. Now recall that we previously had octets, right, for our IPv4. That's because each field or section in the IPv4 address was 8 bits. Now we use hextets for IPv6, and it's because each section is 16 bits. Each section is separated by a colon. So over on the right, we have an example IPv6 address here. The IPv6 address is written in hexadecimal. Hexadecimal includes 0 through 9 and the letters A through F, allowing for 16 characters, 0 through 9 and A through F, which means that each character is 4 bits. And recall our binary counting, right? If we have 1, 1, 1, 1, this is the 1's place, the 2's place, the 4's place, and the 8's place. And we add this up and we get 15, which it goes from 0 to 15, meaning 16 possible combinations. And which is why we write 0 through 9 and A through F in hexadecimal, and why that is equal to 4 bits each character. So there are 16 bits per hextet, which is 4 characters. Here we have 2001, colon, 0db8, colon, 0000, many more zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, AB. And this is a 128-bit address field. Now that's a pretty long address. I don't know about you, but I can't go around memorizing or writing that down all the time. So we have come up with some compression rules for IPv6 addresses. And these are that we can remove all preceding zeros within a hextet. And we can also replace contiguous hextets of zeros with a double colon, only once per address. Now imagine, right, that instead of having 3 hextets in a row of zeros, that we only had 2 hextets. And this was actually 1, 2, 3, 4, and here instead of being numbers, that this was actually 0000. So this would end up being 2001 0db8. And let's say we did 0 compression here and we didn't have the once per address rule. So we did : 1234 : and the rest of the address here, 4, 5, 6, 7, etc. Right now, we have no way of knowing how many hextets are zeros in each of these 2 colons. This one might be the 2 hextets and this one's 1 hextet, or it could be vice versa. It's ambiguous, and we have no way of knowing. That's why we can only do that 0 replacement once per address, is so that we are always able to reliably reproduce the address. So to see that in action and taking our long address up at the top here, and we are striking out our preceding zeros within a hextet and replacing all contiguous zeros with a double colon, we are now left with this address here, 2001 db8 : 123 4567 89ab, rather than having all of our extra zeros there. So you might be wondering, with IPv6, how do subnet masks work? How do we separate our host portion from our network portion? And does that even work the same? Well, the answer is it does work exactly the same. It's just a longer field. That we do still separate our host section and our network section by a contiguous set of ones, being a prefix length or a subnet mask. And let's see that a little more in the following slides here. First, the type of addresses. So the global unicast IPv6 address type is analogous to the public IP address space for IP version 4. It is the 2000::/3 space. The unique local is similar to the RFC 1918 address space. Recall our private non-routable address space, our 10 dot and 192.168 dot addresses. This is FC00::7. It's worth noting that given the sheer number of IPv6 addresses available, there's a lot of debate as to whether this unique local address space is even going to be used at all. We might not really use private addresses within our networks. We might just have public addresses assigned everywhere. And we'll see that this is particularly useful and capable with using EUI64, a process to self-assign a globally unique IPv6 address without having any DHCP server and only providing some stateless information from the router. Our link local address is not routable whatsoever. This is very akin to a MAC address. However, it exists up at layer 3 with IP version 6. This is the FE80::/64 address. The link local is only used for communicating with other devices on your same broadcast segment, in the same broadcast domain. It's not routable whatsoever. And as I mentioned, it's very akin to the MAC address at layer 2, but it is the layer 3 address. There is the Anycast IPv6 address type. This is the same as the global unicast address type. Same range, the 2000::3, but it's one address can belong to multiple nodes to allow, instead of a one-to-one, but a one to closest. and we'll take a look at that a little more in the following slide. The multicast address range is FF00::/8, where unicast is 1 to 1, multicast is 1 to many, and anycast is 1 to closest. And the modified EUI64, that this is the process used to self-assign a globally unique IPv6 address. The most common prefix length is a /64. And think there is a 128-bit address field, which means a /64 would leave us with 64 host bits. This is a huge number of potential host addresses in a /64. And a /64 is even recommended on point-to-point links due to its compatibility with EUI64. We're throwing away trillions and trillions of addresses on point-to-points because it's easier to use. And that can really give you a sense of just how many IPv6 addresses there are, that it's recommended as best practice to use /64s just about everywhere. So I know I very briefly touched on anycast and multicast as being 1 to 1 and 1 to closest and 1 to many. Let's take a little closer look at that here. So anycast versus multicast. Our multicast is 1 to many. It's one speaker here potentially speaking to many other speakers or many other receivers. That our D here can speak to A, B, and C all at the same time, of being one speaker to many receivers, whereas anycast is 1 to closest, where we see here if we have our D node in the cloud and it's sending traffic with a destination of this address, well, all 3 of these ABC servers have the same address. It's just the cost to get there is lower for one of them than the others, so it will take the closest one. It uses the same addresses as the global unicast, so these are global unicast addresses. They're just assigned to multiple devices so that you will be routed appropriately. Consider planet Earth, right? And I'm over here. Okay, say I can't draw North America, but that's North America. And there we got Europe and Africa. Say I'm over here in North America and I have a server I'm trying to access that has a presence in Canada and over in Europe and down in Africa. I sure hope that I will be directed to my Canadian server. However, let's say that Canadian server goes offline and my internet provider has a 100 gig connection down to Africa, but only a 1 gig connection over to Europe. Well, the lowest cost then would be to go down to Africa to get to my server there, is that the cost is directly related with bandwidth. It is also a manually configurable item and is a much more complex subject that is outside the scope of the JNCIA, but all 3 of these servers that I'm trying to access could all have the same address, 1.1.1.1. And if one of them goes down, or say I move and I'm now over in Spain, that I should be directed to the European address or the European location for that server. Now, the exam topics do include IPv6 multicast, which leads me to believe that you'll be expected to know some of the well-known multicast addresses. Here are 4 of the most common ones that I recommend you commit to memory. FF02 is the first 4 characters of each of these, and it's just the last character that changes. FF02::1 is all IPv6 devices. This is the same thing as a broadcast, except it is a multicast, and all IPv6 devices are expected to be listening in on that multicast address. ::2 is all IPv6 routers. All routers that are capable of routing IPv6 addresses should be also listening on this multicast address. ::5 is all OSPF v3 routers. That is the OSPF protocol that is specifically for IP version 6, and ::A is for all EIGRP v6 routers. So all routers that are EIGRP routers for IP version 6. Excellent. I really appreciate you going through this with me. I hope that this has been informative for you, and I would like to thank you for viewing.